Alright, so I'm just going to jump right into section 4.2 and talk about the first thing that pops up in the section, which is an exponent of 0. It's pretty common for students or people to say anything to the 0 power is 1. And that's true, but in a purely mathematical sense that's true, but it may seem like we're violating that rule in some of these problems. And I'll try to help you be careful. If you just blindly, every time you see a 0 exponent, write down a 1, you're not going to get everything right in this section. First of all, maybe I should show where a 0 exponent, how a 0 exponent could come up. If I gave you a problem like this, again, this is just warm up before we get into the handout itself. In section 4.1, we learned that we could simplify this problem by subtracting the exponents. And if I subtract the exponents, there's a tie between the exponents, so I could actually leave the 2 in the numerator or the denominator when I do the subtracting. Because I don't like fractions, I won't write it as a fraction. So I can say this is 2 to the 3 minus 3 power by using the rules that if I'm dividing terms with the same base, I subtract the exponents. And all of a sudden this reduces to 2 to the 0 power. So 0 powers can come up when you're subtracting exponents. And if I did this problem on my calculator, which is almost insulting because anything divided by itself is 1. Really? Really? Hold on, I've got my calculator in some funky mode right yet. Mode 1. Good. Fix. But if I did this on my calculator, 2 cubed over 2 cubed, I'd find out that it equals to 1. So when I reduce this, I know that this equals to 1 because this is 8 over 8, which is 1. And reducing the problems using different techniques, the different techniques have to produce answers that are equal to each other. So this is a way to show that at least that 2 to the 0 power is 1. And I can do a bunch of things on my calculator. If I just raise nice positive integers to the 0 power, if I did 5 to the 0 power, 6 to the 0 power, or 7 to the 0 power, these kind of fit the mold that anything to the 0 power is 1. Each one of these, if I did 5 to the 0 power, that's equal to 1. 6 to the 0 power, that's also equal to 1. And 7 to the 0 power, that's also equal to 1. The subtleties with this rule, the times where I could have something to the 0 power and not get a 1, is when I start to have multiplication and negatives around. And if you're going to make a mistake with the 0 exponent, it's going to be blindly writing down 1 for things that aren't equal to 1. These next 3 problems, how about negative 7 to the 0 power, negative 6 to the 0 power, and negative 5 to the 0 power, they sure look like they all should be 1, but this is not the case. Each one of these is going to equal to negative 1. If I do each one of these on my calculator understands the subtlety that makes these 3 problems different than the last 3. But if I did negative 7 to the 0 power, this is negative 1. If I did negative 6 to the 0 power, well, did it right, be okay. Negative 6 to the 0 power is negative 1, and negative 5 to the 0 power is also negative 1. It feels like I'm violating the rule that anything to the 0 power is 1, but I'm not. It looks like I'm raising negative 7 to the 0 power here, negative 6 to the 0 power, and negative 5 to the 0 power, but I'm not. Each one of these problems, because the negative is not in a parentheses, that negative means the opposite of 7 to the 0 power, or negative 1 times 7 to the 0 power. So what my calculator understands is the only thing that's being raised to the 0 power is the 7 in the top problem, the 6 in the bottom problem, or middle problem, and the 5 in the bottom problem. Because that negative 1 is not in a parentheses, the exponent doesn't apply to it, and the only thing the exponent applies to is the 0, or is the 7, the 6, and the 5. So this top problem really means negative 1 times 1. The rule that anything to the 0 power is 1 holds, because the thing that's being raised to the 0 power is the 7. Similarly, the middle problem here really means negative 1 times 1, which is negative 1, and the bottom problem means negative 1 times 1. So if we have a negative in a 0 exponent, we're not guaranteed to get a 1. These three problems, which look something like the problems right above them, have the negative in a parentheses, and all of a sudden when the negative is in a parentheses, then I get 0 again, because now it's not, this is negative 1 times 7 to the 0 power. It's not negative 7 to the 0 power, even though it looks like it. In these three, it is the whole negative numbers raised to the 0 power, and each one of these is going to be 1. So this is going to be 1, this is going to be 1, and this is going to be 1, because the negative isn't separate from a 7. This is just raising a 7 to the 0 power, multiply and finding the opposite of it, raising 6 to the 0 power and finding the opposite of multiplying it by negative 1. So when the negative's not in a parentheses, the exponent doesn't apply to it. I'm not actually raising a negative number to the 0 power. Whereas in these three problems, with the negative in a parentheses with a 0 outside, I'm raising the negative 7, the negative number to the 0 power. So and I can show you on this. So here's negative 7 to the 0 power, which is positive 1. Here's negative 6 to the 0 power, which is positive 1. And negative 5 to the 0 power, which is all positive 1. So with nice positive numbers without negative signs, anything to the 0 power is easily 1. When we have negatives, if a negative is not in a parentheses, then the answer is more than likely going to reduce to a negative 1. But negatives inside a parentheses and you have a 0 exponent, the answer is going to more than likely reduce to 1. The only other thing with 0 exponents, we could have problems like this. How about like 3 times 2 to the 0 power, about 4 times 5 to the 0 power, and 6 times 7 to the 0 power. These should be easier, because it should be clear that the only thing that the exponent applies to is the number to the right of the times sign. This top one is really 3 times 1, which is 3, because the exponent doesn't apply to the 3. In the middle one, the exponent only applies to the 5. 5 to the 0 power is 1, and this is 4. And the bottom one, this is 6 times 1, which is 6. And again, I'll show all these on my calculator. The nice thing about doing problems without letters is they're easy to do on my calculator. So 3 times 2 to the 0 power is 3. 4 times 5 to the 0 power is 4. And 6 times 7 to the 0 power is 6. If I took each one of these three problems and introduced a parentheses, I could change the results. So these three problems, 3 times 2 to the 0 power, 4 times 5 to the 0 power, and 6 times 7 to the 0 power, well, these are all equal to 1, because if I was doing orders of operations and wasn't doing this on my calculator, I do parentheses first before the exponents. So this would really be the same as 6 to the 0 power, which would be 1. This would be 20 to the 0 power, which would be 1, because I do exponent parentheses before exponents. This would be 42 to the 0 power, which is 1. And again, I do all these on my calculator because I don't have letters. So I'm going to go 3 times 2 to the 0 power it's 1. 4 times 5 to the 0 power, it's 1. And 6 times 7 to the 0 power, it's also 1. So parentheses are a big deal when we have 0 exponents. If everything in a problem is inside a parentheses with a 0 exponent outside the parentheses, then your answer is going to simplify to 1. If we don't have parentheses and we have 0 exponents and we have negative signs or numbers multiplied by the term with a 0 exponent, then the answer is more than likely not going to be 1. So I have to be careful, not so much when I just have a single positive number to the 0 power. That's not kind of the confusing part of 0 exponents. The confusing part of 0 exponents are when we have negatives, whether they're in front of a parentheses or inside a parentheses. Negatives in front of a parentheses is probably going to reduce to -1. Negative inside a parentheses is going to reduce to 0 to 1. If we have multiplication without parentheses, it's probably not going to reduce to 1. Multiplication inside a parentheses with a 0 exponent is going to be 1. So that's kind of the beginning of section 4.2. The first 12 problems deal with with 0 exponents. And it's kind of the easier part of 4.2. I did kind of everything I needed to. Hopefully you could run through and do the first 12 problems without me prompting you, because 0 exponents with letters work the same as 0 exponents with numbers, meaning if I don't see a negative or parentheses or multiplication, I can easily put 1. The first 2 problems that I see, 2 and 4, because there isn't a negative sign in front of the numbers, there isn't a parentheses, these are just standard just 1s, and they're not subtle at all. It's like the problems I did on the first page where I didn't have any parentheses, multiplications, or negatives. The top one I couldn't do on my calculator, the bottom one I could, but I don't need my calculator to do 0 exponents. The next 2 problems, 6 and 8, they both have negatives. Neither one has a letter, so both of these I could do on my calculator. So if you're not sure what the answer to 6 is, or if you're not sure what the answer to 8 is, then you can just blindly press buttons on your calculator. It's not going to let you down if you enter it properly. The top one, number 6, the answer is going to be -2, because the negative is not in a parentheses. The 0 exponent only applies to the 2. The 2 to the 0 power is 1, but when I multiply it by that negative, which is really like a -1 times, I get -1. Whereas problem 8, the negative being inside the parentheses, the whole negative number is being raised to the 0 power, and that's equal to 1. And again, you could do both of those on your calculator. You could do -2 up arrow 0 without a parentheses and get -1, and you could do -3 up arrow 0 inside a parentheses and get 1. It's when we have the variables or the letters that you have to be a little careful. So 10 and 12, neither I can do on my calculator, and they both have a 0 exponent, and I have to decide if they're both equal to 1, if one's equal to 1 and one's not equal to 1, and these are supposed to compare to the problems I did on this sheet. They're not exactly the same because the problems I did on this sheet didn't have the variables, but they are in some sense the same. They kind of structurally are the same. The top one, 4 times b to the 0 power, that's not that different than 3 times 2 to the 0 power. Or 4 times 5 to the 0 power is even more like it because it still has a 4. Because the 4 is not in a parentheses, the 0 exponent doesn't apply to the 4. It only applies to the b. And so this is really, if I want to emphasize, this is 4 times b to the 0 power. The 0 exponent only applies to the b. The b to the 0 power is equal to 1, but the 4 isn't raised to the 0 power, so it's multiplied by that 1. And the answer to this is 4. And in problem 12, the whole quantity, 3ab, is being raised to the 0 power. I can't simplify 3ab like I could the 3 times 2 or the 4 times 5 or the 6 times 7, but but still everything is being raised to the 0 power, and there isn't anything outside the exponent. If I want to, this whole thing equals to 1. If I want to, I could simplify this like I did in section 4.1. This is really 3 to the 0 power, a to the 0 power, b to the 0 power. I could raise everything inside the parentheses to that 0 power, and all three of those pieces is 1, and the whole thing reduces to 1. So ultimately, this is just 1. That's the first thing we have to remember. And like I said, it's the easier of the things to remember. The harder of the things to remember are negative exponents. And although you're supposed to know how to do negative exponents already, a lot of students do horrible with negative exponents. Negative exponents, I'll say, rarely reduce to negative numbers. And I can say negative exponents usually reduce to fractions. Negative exponents can come up if you use the rule where you're dividing terms with the like bases by subtracting the exponents, and you don't do what I did in section 4.1. For instance, if I had 3 to the 2nd power over 3 to the 6th power, when we simplified this in section 4.1 or something like this, we would have subtracted the exponents and left the term in the 3 in the denominator, because the bigger exponent's in the denominator, and then I could do this, and it simplifies to 1 over 81. I didn't have to do what I did. I simplified the way that I simplified to avoid negative exponents. It is completely legal to just subtract the exponents and not write a fraction. So I could treat this something like, 2 to the 4th power over 2 to the 3rd power. I get 2 to the 4 minus 3 power and don't get a fraction. You can always, if you're dividing terms with the same bases, just subtract the exponents and avoid the fractions. But if you avoid the fractions in every case, you could run into negative exponents. If I simplify this by subtracting exponents and not reducing a fraction, not making it into a fraction, I'd get a negative exponent. This negative exponent turns into 1 over 81. As a matter of fact, I can show you both of these on my calculator. If I did 3 to the 2nd power over 3 to the 6th power, that reduces to 1 over 81. And if I did 3 to the negative 4 power, that also reduces to 1 over 81. They're equal to each other. So I'm going to write a handful of base problems down with negative exponents just to get you used to the big rule for negative exponents. So I'm going to write down 5 to the negative 2, 3 to the negative 3, 4 to the negative 5, and 6 to the negative 1. So each one of these problems has a negative exponent, and if I reduced each one of these on my calculator, I'm not going to get a negative number for any one of them. So let me do all my calculator first, and then I'll show you how to do them without your calculator. So the first one, 5 up arrow negative 2 power. My calculator tells me that this is 1 over 25. 3 up arrow negative 3 power. My calculator tells me that that's 1 over 27. 4 up arrow negative 5 power. My calculator tells me that's 1 over 1,024. And then 6 up arrow negative 1 power. My calculator tells me that's 1/6. That's getting harder to see. You'll notice that every term number here with a negative exponent reduced to a fraction with a 1 in the numerator. And that's a general rule for negative exponents. If you had, well, in general, we'd say this: x to the negative n power equals 1 over x to the n power. So if I have a number raised to a negative exponent, and that's the whole problem, I can make that exponent positive by creating a fraction with a 1 in the numerator, and I can make that negative exponent positive in the denominator. So 5 to the negative 2 power is 1 over 5 squared. The 5 squared is 25, so that's 1/25. 3 to the negative 3 power is 1 over 3 cubed, and 3 cubed is 27, so that reduces to 1 over 27. 4 to the negative 5 power is 1 over 4 to the 5th, and I imagine 4 to the 5th is 1,024. That's why that reduces to 1,024. And then 6 to the negative 1 power is 1 over 6 to the first power, which is 1 over 6. If I did this with letters, like if you had x to the negative 3 power, or y to the negative 8 power, or z to the negative 9 power, each one of these is just kind of has a single base raised to a negative exponent. Couldn't do any one of these three with my calculator, but I can rewrite each one of these with a positive exponent. X to the negative 3 power is 1 over x cubed, y to the negative 8th power is 1 over y to the 8th, and z to the negative 9th power is 1 over z to the 9th. That's the easy part of working with negative exponents. There's a lot more in this section that we're going to do, and most everything I do in this section it can be done with rules of exponents and nice algebraic techniques, but I'm going to basically shortcut everything in this section, because the shortcutting is what people do, and it's a lot easier than doing simplification by rules. So I'm going to jump into the section and do the first couple problems, and then I'll have to stop and help you figure out how to do the next couple. Yeah, so we'll do just kind of two at a time. We'll do two problems, and then I'll make up some examples that will help you understand how to shortcut your answers for the next couple. So 14 I can do on my calculator. It says simplify right with positive exponents. I know ultimately the answer to 14, because it doesn't have a letter I can get on my calculator. The answer to this is supposed to be 1/8. So 2 to the negative 3 power is supposed to be 1/8. I'm supposed to realize that I can write 2 to the negative 3 power as 1 over 2 cubed, and because 2 cubed is equal to 8, this is the same as 1/8. 1 over 2 cubed would be a correct answer, but anytime I have a number with an exponent, I'll try on my calculator to see if I can easily write that number without the exponent, and it's definitely not a nuisance to write 8, so 1 over 8 is better than 1 over 2 cubed. For 16, I'm asked to rewrite the problem, simplify it, write it with positive exponents. I'm just going to write this as 1 over b to the 4th. Again, these are base simple problems. The next few problems have negative exponents in a denominator, and let me show you how to work with those. Again, this is going to be outside the text a little bit. Let's try to do 3 over 2 to the negative 4th power, 6 over 5 to the negative 2 power, 4 over 3 to the negative 2 power. So I'm going to try each one of these first on my calculator just to know what the answer is, and then I'll show you how to get it without your calculator, because once the problems have letters, my calculator's not going to help me out. So top one, 3 over 2 to the negative 4th power is supposed to equal 48. I have a negative exponent, and all of a sudden my answer is not a fraction, so that's kind of when I said negative exponents usually give me fractions. It's not always, but they rarely give me negative numbers. I don't see a negative number here. The middle one, 6 over 5 to the negative 2 power is 150. It's not a fraction again, but at least it's not a negative number. And the bottom one, 4 over 3 to the negative 2 power is 36. So if you're clever, maybe you figured out how to do the problems without your calculator. The nice thing about problems that have negative exponents is it's real easy to make negative exponents positive if there isn't any adding or subtracting in the problem. In the first problems, I didn't have a fraction. I got rid of my negative exponent by creating a fraction and moving the term with the negative exponent to the denominator. I'm going to do the reverse. If you have a negative exponent in a denominator and there's no adding or subtracting in the problem, you can get that negative exponent to have a positive exponent if you move the term from the denominator to the numerator. So in this first problem that I made up, I can do this without my calculator if I take the 2 to the negative 4th power and I move it to the numerator. Once I've stole the 2 from the denominator, I don't need to write a fraction anymore because I've taken away the entire denominator. 2 to the 4th power is 16. So this whole thing is equal to 3 times 16. And 3 times 16 is 48. Similarly, the middle problem I can do by writing it with a positive exponent. I could take the 5 to the negative 2 power, make its exponent a positive 2 by moving the 5 from the denominator to the numerator. I've taken the entire denominator of the fraction, so I don't need to write a fraction anymore. Now I have orders of operations in terms of my simplifying. I'm going to do the exponent first. 5 squared is 5 times 5, which is 25. So this whole thing reduces to 6 times 25. And 6 times 25 is the 150 that I knew it should be. The bottom problem, same deal. I'm going to make the exponent positive. If I'm working without my calculator, I just can't work with negative exponents, so I make my negative exponent positive. Taking the 3 from the denominator to the numerator, I don't need to write a fraction anymore. If I'm simplifying this without a calculator, I do the exponent first. 3 squared is 3 times 3, which is 9. And then 4 times 9 is 36. So these are the answers. Because the problem was lacking letters, I could bust out the answers without my calculator. These 3 problems will have the exact same skill as problems 18 and 20. So theoretically, I should be able to give you a few minutes and you should be able to do both problems 18 and 20. The fact that they have letters, I can't do them on my calculator, but I can write something that's equal to the original problem that doesn't have a negative exponent. And I'm going to do exactly for 18 and 20 what I did for the 3 problems when I did them by hand. I'm going to take the term with the negative exponent and move that negative exponent from the denominator to the numerator. I'm not going to leave a fraction anymore because I've taken the entire denominator. Problem 18, I can rewrite it as 1 times w to the 5th, and I can just write that as w to the 5th because 1 times anything is itself. So probably for a nice answer for 18, I would write just w to the 5th. I could do the same thing for 20 that I did for 18 that I did for the last 3 problems that I did by hand. I can make this 3 times z to the 6. It wouldn't be wrong to have the times sign, but if I wrote the 3 and the z to the 6 next to each other without a times sign, it still would mean the same, and it's written with less symbols, so it's better. So again, I've done a bunch of problems so far. I've done probably 12 problems between the ones I made up and the ones in the handouts, and I haven't seen a single negative answer. And that's completely going to hold. That when I'm working with negative exponents, it rarely reduces to negative numbers. It usually reduces the fractions, but that usually is probably even a bit strong. It kind of depends how the problem is set up. All right. So the next few problems, again, I'm going to try to motivate how to do the problems by making up problems that we can do in our calculator. So let's try this. 3 times 2 to the negative 3 times 4. How about this? 2 to the negative 3 times 5 times 3 to the negative 1, and how about 6 to the negative 2 times 4 to the negative 1 times 8 squared. So each one of these problems I should be able to figure out what it equals to just by blindly pressing buttons, because each one of these three problems is lacking letters and my calculator smokes these. So I'm going to do each one of these three, figure out what they equal to, and then talk about, if I didn't have a calculator, how I might try to reduce them. So top one, 3 times 2 up arrow negative 3 times 4. So these aren't in the handout. These are just supposed to motivate the next few problems. So this reduces to 3/2. The middle one is 2 to the negative 3 times 5 times 3 to the negative 1. It reduces to 5/24. And the bottom one, 6 to the negative 2 times 4, 6 to the negative 2 times 4 to the negative 1. This is going to be, I can't even enter it. 6 to the negative 2 times 4 to the negative 1 times 8 squared. 4/9. Whoa. So, question is, how could I get those three answers without using my calculator? And it's not that hard, actually. In these problems, I have no fractions and I have negative exponents. What I'm going to do for each one of these problems is I'm going to create a fraction. And the thing that's going to work its way to the denominator is the term with the negative exponents. The terms without exponents or with positive exponents are going to stay in the numerator. So if I was doing this top one by hand, I would say this is 3 times 4 over 2 cubed. I'm going to take the 2 to the negative 3 power and move it to the denominator. The 3 and the 4 didn't have negative exponents. They don't go to the denominator. And then I can reduce this. The 3 times 4 is 12. 2 cubed I know to be 8, but if you didn't know 2 cubed was 8, this reduces to 12/8. And then 12/8 must reduce to 3/2 because 12 divided by 4 is 3, 8 divided by 4 is 2. So from the problem to the answer without my calculator, I work so poorly with negative exponents, I'm going to make the negative exponent positive, and then I'm going to reduce. The middle problem, same deal. If I didn't have a calculator that was so easy to use, I would rewrite this as 5/2 cubed times 3 to the first, because the 2 and the 3 had negative exponents. If I want to make their negative exponents positive, because they're not in a denominator of a fraction, they're in a non-fraction, I'm going to pop them down to the denominator of a fraction. And then if I did the rest of this, to simplify it, 2 cubed is 8, 3 to the first power is 3, and you can see the 5/24 nicely, that fraction doesn't reduce. Third one's the hardest to do in terms of the reducing part, but it's not that hard to get the negative exponents positive. If I wanted to rewrite the third problem, I'd rewrite this as 8 squared over 6 squared times 4 to the first power. I take the terms with the negative exponents, bring them down to the denominator of a fraction, and then if I wanted to go further, 8 squared is 64, because 8 times 8, 6 squared is 36, 4 to the first power is 4, 36 times 4 in the denominator is 144, so this comes out to be 64/144. Apparently that reduces by 16. I'm not going to attempt to reduce that by 16, but 64 divided by 16 is 4. 144 divided by 16 is 9. If I did 64/144 on my calculator, I'd still get that 4/9. So the important part of this page is to know how to take a problem that only has multiplication, that has negative exponents, but not with all the terms, to turn the problem into something with positive exponents. And how do I do that? I only move the terms with the negative exponents. If a term doesn't have a negative exponent, if it doesn't have a exponent, it means it has an implied exponent of 1. And if its exponent is clearly positive, it doesn't move. So when I'm rewriting terms, writing problems that have negative exponents and no addition or subtraction with positive exponents, if I don't have a fraction, I have negative exponents, I'm going to move the terms that have the negative exponents into the denominator and make the exponents positive. So that is supposed to motivate you to figure out how to rewrite 22 and 24 with only positive exponents. And very specifically, on 22, I'm only going to move the x. On 24, I'm only going to move the x. So when I go to rewrite these problems, I can't simplify them to get rid of the letters, but I can write a problem that's equal to the original problem that doesn't have a negative exponent. 22 can be rewritten as 3 over x to the 4th power. 24 can be written as 4y squared over x cubed. We're getting close to the end of the tricks with negative exponents, but we're not done with them yet. Next trick with negative exponents that we have to remember. I'll do a few problems and help you remember that trick. About like this: 2 over 3 to the negative 4 power, or 3 over 5 to the negative 2 power, or 6 over 7 to the negative 1 power. Is that enough for these problems? 4 squared over 5 cubed to the negative 2 power. So each one of these problems I made up. It's not from the handout, but they're friendly problems in that I can bust them out in my calculator. So I'm going to do each one of these on my calculator. So top one, parentheses, fraction, 2 over 3, parentheses, exponent, negative 4. The top one is supposed to equal to 81 over 16. Do the second one now, parentheses, fraction, 3 over 5, parentheses, exponent, negative 2, reduces to 25 over 9. The third one, parentheses, fraction, 6 over 7, parentheses, exponent, negative 1, comes out to 7 over 6. And the bottom one, parentheses, fraction, 4 squared over 5 cubed, parentheses, exponent, messed up, parentheses, fraction, 4 squared over 5 cubed, get out of the denominator, 2 right arrows I needed, parentheses, exponent, negative 2, and this one's supposed to equal, oh my gosh, 15,625 over 256. That's really not such a nice number. So I've simplified each one of these, but that wouldn't help me in terms of doing a problem if it had a letter. Each one of these problems, what they have in common is there's a fraction with a negative exponent, and the shortcut to make a negative exponent positive when it applies to an entire fraction is to take the reciprocal of the fraction. So the top one I can rewrite as 3 halves to the 4th power, and then I can raise the 3 to the 4th power and the 2 to the 4th power. 3 to the 4th power gives me the 81, 2 to the 4th power gives me the 16. Second one, same structure, a negative exponent applies to entire fraction. To get the negative exponent positive, I take the reciprocal of the fraction. So 3/5 to the negative 2 is the same as 5/3 squared. And this is going to equal 5 squared over 3 squared. 5 squared is 25, 3 squared is 9. Third one, 6 over 7 to the negative 1 reduces to 7 over 6 to the first power, which is 7 to the first power over 6 to the first power. 7 to the first power is 7, 6 to the first power is 6. So all my work here in black is matching up to my orange answers that my calculator gave me. Last problem I made up, same strategy. I'm going to make this 5 cubed over 4 squared to the positive 2. If I have a negative exponent outside a fraction, I can make the negative exponent positive by taking the reciprocal of the fraction. Now to reduce this, I have to multiply the exponents. So this is going to be 5 to the 6th power over 4 to the 4th power. And this comes from yesterday's, our section 4.1. And then the 5 to the 6th power that I have up in the numerator is at 15,625. And the 4 to the 4th power that I have in the denominator is the 256. So the big trick on this page is if you have a negative exponent that is outside a fraction, to make that negative exponent positive, you take the reciprocal of the fraction, and then you simplify using the rules of positive exponents that we did in section 4.1. So the next two problems I'm going to see, problems 26 and 28, both have negative exponents outside a fraction. Finally, I get a problem without a letter. So 26 I could do with my calculator. But if I didn't have my calculator, I'd write this as 4 over 3 to the 3rd power. And then I'd get 4 to the 3rd power over 3 to the 3rd power. I know that 4 to the 3rd power is 64. I have that memorized. And 3 to the 3rd power is 27. If you didn't have them memorized, you could do 4 to the 3rd power and get 64, 3 to the 3rd power and get 27. Again, the answer is 64 over 27. I didn't even need to do this by hand. I could have just done parentheses, fraction, 3 over 4, parentheses, up arrow, negative 3, and my calculator would confirm that the answer is 64 over 27. 28, because it has the letter, it slows me down. 28, I can write this as 4x squared over 3, all cubed. Get rid of the exponent now, make this 4 cubed x to the 2 times 3 and 3 cubed. The 4 cubed in the numerator is 64. The x is going to wind up with an exponent of 6. The 3 is going to wind up with an exponent of 27. All right. Let me make up one quick problem before I do 30. If I gave you this problem, 2 to the negative 3 power times 2 to the negative 2 power. Again, I could smoke this on my calculator real easily. So 2 up arrow negative 3 times 2 up arrow negative messed up negative 2. I get 1 over 32. So I should be able to get 1 over 32 without using my calculator. And there's multiple ways to get there. So if you're working ahead of me on this problem and without your calculator you were able to get 1 over 32 and you use this technique different than mine, then you're completely okay. What I'm going to do to get this might be different than yours. But I don't like negative exponents. I can get rid of negative exponents quickly. 2 to the negative 3 is 1 over 2 cubed. 2 to the negative 2 is 1 over 2 squared. So I can write each of the pieces with a positive exponent. Now I'm multiplying fractions. When you multiply fractions, you multiply the numerator. So I get 1 times 1 over 2 cubed times 2 squared. When you multiply fractions, you multiply the numerators, you multiply the denominators. The numerators are easy. 1 times 1 is 1. The denominators are also easy. If I'm multiplying terms with the same base, I add the exponents. So I get 1 over 2 to the 5th, and that 2 to the 5th is 32, so that's 1 over 32. That's how I could do this problem and get it reduced to a problem with positive exponents, which is the answer my calculator gives me without, this is how I could do it without my calculator if I knew 2 to the 5th was 32. So problem 30, if I wanted to do this, I can write this as 1 over y squared. I don't need a times sign, but I'm going to write a times sign because these are implied to be times 1 over y cubed. So this is going to be 1 over y to the 5th, because in the numerator you multiply the 1's. In the denominator you multiply the y's. And when you multiply the y's, you add their exponents. 32 I just kind of snuck in here. 32 is a problem that was really more appropriate from section 4.1, but we can't forget the basic things we did from section 4.1. This problem doesn't have any negative exponents, and if it was in section 4.1, I would have probably gave the y in the numerator an exponent of 1 because it has an implied exponent of 1. I'd subtract the exponent and leave the y where the bigger exponent was. The bigger exponent's in the denominator. And I'd subtract the exponents, leave the y in the denominator, be forced to have a fraction answer, so I'll leave a 1 in the numerator. Those I can't do. Alright, so I need to make a few more problems up with numbers so you can see how 34 and 36 can be done. So a few more problems, nice easy ones. 3 to the negative 2 over 2 to the negative 3, and then how about 3 to the negative 4 over 2 squared, and 2 to the negative 3 over 5, oh, not that one, 2 to the 3 over 5 to the negative 2. So I made up 3 problems, straight fractions with negative exponents. I'm going to do each one on my calculator first. Top one, 3 to the negative 2 over 2 to the negative 3. This one's supposed to equal to 8 over 9. Middle one, fraction 3 to the negative 4 over 2 squared. This one's supposed to equal 1 over 324. Bottom one, 2 cubed over 2 cubed over 5 to the negative 2, 200. So each one of these problems started off with a negative exponent. 2 of them turned into fractions, 1 didn't. The question would be, how could I get the answers if I didn't have a calculator to tell me what the answer is? The best way to get the answer is to make the negative exponents positive. When we have fractions and we have negative exponents, we can make any negative exponent positive by moving it to the opposite side of the fraction, as long as there's any adding or subtracting, and there isn't in any of these problems. So if I was doing this by hand, both the 2 to the negative 3 and the 3 to the negative 2 had negative exponents. I'm going to move them to the opposite side of the fraction. The 3 is going to go down, the 2 is going to go up. I'm going to change their negative exponents from negative to positive. And now in the numerator I have 2 cubed. 2 cubed is 2 times 2 times 2, which is 8. In the denominator I have 3 squared, which is 9. Again, you could do 2 cubed and get 8, and 3 squared and get 9 if you didn't want to use your calculator. Or if you didn't know how to do it without a calculator. Next problem, a little bit different because there's only one negative exponent. If you look at my answer, it has a 1 in the numerator. It's going to be easy to get that 1 in the numerator because when I write this with positive exponents, only the 3 to the negative 4th moves. The 2 squared is going to stay in the denominator because it doesn't have a negative exponent. I don't need to move it. If I moved it up to the numerator, I'd have to give it a negative exponent. From this fraction, I've vacated the numerator. I can't write a fraction without a numerator, so I'm going to leave a 1 behind. And now I have 1 over 2 squared times 3 to the 4th. 2 squared is 4. 3 to the 4th, I think, is 81. 3, up arrow 4 is 81. So the denominator turns into 4 times 81. So I get 1 over 4 times 81, and the 4 times 81 is the 324. The third problem I put on this sheet, the answer is not a fraction. That's because if I take the time to make the only negative exponent positive, I bring the 5 up from the denominator to the numerator. I'm not going to move the 2 down because it doesn't have a negative exponent. I'm only moving terms with negative exponents. Top one I had to flip each. The middle one I only move the numerator down. The bottom one I only move the denominator up. And if I did this on my calculator, or without my calculator, 2 cubed is 8, 5 squared is 25, and 8 times 25 is 200. Alright, so these 3 problems are supposed to motivate you to be able to solve these problems. I don't know that they're easier or harder, but they're just different. So for both 34 and 36, I'm not comfortable working with negative exponents. I'm going to make my negative exponents positive. On 34, I have to move both pieces because they both have a negative exponent. So I'm going to rewrite this as z to the positive 6 over z squared. And now I'm supposed to be able to reduce that because I know the rules of reducing from section 4.1. So all the rules that we're getting will keep coming back to us and get more complicated as the sections go on. So this is just going to be you subtract the exponents. I don't need a fraction in my answer because the bigger exponent's in the numerator, so I get z to the 4th. If I was doing 36, I'm only moving the z to the negative 3 up. When I move it up, I make its exponent positive. And I'm left with z cubed times z cubed. I don't get a fraction anymore because I've stole the entire denominator. These z's are being multiplied, so I add their exponents. And this answer would be z to the 6th. Getting closer to the end here. Oh, we only do have one problem left. I guess we're at the end. So this is kind of 3 problems in one. If I want to reduce 38, I'm going to deal with the fraction 24 over 36, the fraction x over x cubed, and the fraction y to the negative 2 over y. The first 2, I don't need to worry about negative exponents. The last one I do have a negative exponent I need to deal with. So 24 over 36, I can reduce that without my calculator. But if I use my calculator, it's going to tell me that reduces to 2/3 because they both divide by 12. So in my answer, I'm going to have a 2 in the numerator, a 3 in the denominator from reducing to 24 over 36. For the x's, they don't have negative exponents, so I don't need to move an x. I do need to know that the numerator had an exponent of 1. And now I'm going to subtract the exponents because if you're dividing with the bases the same, you subtract the exponents. You leave the letter where the larger exponent was. So I'm subtracting the exponents 3 and 1, and I'm getting the x to the denominator. For the y's, I'm going to move the y squared from the numerator to the y to the negative 2 from the numerator to the denominator. And I'm going to combine the y's. The y in the denominator had an exponent of positive 1. That's why it didn't move. Now the y's are on the same level. They're on the denominator, but they're being multiplied. So the y in my answer is going to wind up in the denominator because both y's are in the denominator. There's no reason to have a y in the numerator. The y's are being multiplied. I'm going to add their exponents and get a y to the 3rd power. So the answer to problem 38 that I should get, I don't need to have that 1 in the numerator because I already have something in the numerator, is 2 over 3x squared times y cubed. So that's the entire even problems of the section with a bunch of calculator problems thrown in just to help you through the rules of negative exponents that you just might have forgotten. Technically, everything in this section was supposed to be a review. It may or may not feel like a review. When we do section 4.3, these rules of exponents won't come up really at all, but in 4.4 they're going to come back kind of with a vengeance. All the rules for manipulating negative exponents, turning them positive, whether you multiply exponents, add exponents, or subtract exponents, will all come back in 4.4 with negative fraction exponents. So it's going to be real important to have 4.1 and 4.2 perfectly understood. If you aren't perfectly clear on how to do every problem in 4.1 and 4.2, you're going to get slowed down quite a bit when we get to 4.4. So really, really focus on these sections. Make sure you can do every single odd problem just effortlessly, and that will really add to your success in 4.4. All right, that's going to be enough for now.